Welcome back to another video. Last video we discussed about systems of equations with matrices and also the kernel of a matrix. And today we are gonna do some examples with these. And so the first example, we are given this system of equations, and they tell us to solve this system of new equations. So as I mentioned before, you've probably done systems of equations and solving them, um, and your own methods like elimination or other methods you have probably used. But in this one, we're going to mainly focus with matrices because this is linear algebra. And so, as I mentioned last video, you could write any system of linear equations in the form of ax is equal to b, where A is just a matrix of constants and X is your unknowns in column vectors, and your B is another column vector that's in the right side. So your basically your answers. So to write this into matrix form, because we have three equations and we have three unknowns, this would be a 3 by 3 matrix. So our A is going to equal to 1, 1, 2, negative 1, 2, 1, and 1, negative 1, 2. X would be our variables, x, y, and z. And then lastly, our B is going to equal to our answers. And so we previously we discussed about solving these systems in terms of using row reduction. And so the way we can do this is by putting two of these into an augmented matrix. And so what we're going to do is we're going to combine quote unquote combine matrix A and B, and this would basically be our augmented matrix, which is denoted as A with a line in the middle, B. And so all we have to do is just substitute our A and B. So this would just pretty much be 1, 1, 2, negative 1, 2, 1, 1, negative 1, 2, then our line, and then 3, 0, 9. And so now we have our augmented matrix. And then from here, we can begin doing the row reduction. And as I mentioned before, there are three things that you can do with row reduction. You could change the position of two equations, multiply one equation by some scalar constant that is not 0, and then add one equation with the multiple of another. And then I also mentioned that we want to get this in row reduced echelon form, which basically means as simple as possible. And basically the simplest matrix that we can get would be a diagonal matrix of just ones. So this is the ideal case in which when we do row reduced echelon form, we get this. But obviously, there will be some cases where this will not be true, and then other cases where it's pretty much 100% impossible to get this. And we'll look at that in another example. And then what ends up happening is if we put this in row reduced echelon form, our right side of the augmented matrix, ABC, would actually equal to our answers to our unknowns. In other words, what's in the right, A, B, and C, would equal to X, Y, and Z. And so this is one of the reasons why row reduction can help solve systems of equations. Um, and then also do some other things in case there are some systems that have infinite many solutions, but we'll get to that later. And so what now we're going to do is put this again in row reduced echelon form. And so what we want to do is pretty much have this entire first column be exactly what how this one is. So that means we need to get rid of the 1s and the 2. And like I mentioned before, we have 3 things that we can pretty much do. And so what we're going to do is we're just going to get rid of this 1 right here by simply subtracting the 2 rows. And so what I'm doing here is I'm writing the steps of what I did to get from this matrix to this one. It makes it easier for anyone that's looking over your work to see what you did, and makes it again also easier to find a mistake in case you have any. In my case, it's gonna probably be a lot, because I mean it will get to the point where you you sometimes forget how to you sometimes forget to add or subtract or multiply some things, and it just kind of throws everything off. But hopefully this doesn't happen in this example. So yeah, so we're going to subtract row 2 and row 1. So we get a new row 2. And so what that means is our row 3, bottom row, just stays the same. And so does our first one, because the second one is the only one that's being changed. And so now what we have here is we have 1 minus 1, and then 2 minus -1, and then -1 minus 1. So the 1 minus 1, obviously that'll be 0. The 2 minus -1, which would be 2 plus 1, which is equal to 3. And then the -1 minus 1 would be -2. And so what you did here, it will be the same thing on the other side of the augmented matrix. So it'll be 0 minus 3, and we will get -3. And so you pretty much have to continue doing this until you get everything in reduced echelon form. So now we're gonna get rid of the this 2 over here. And so what we're gonna do now is we're gonna subtract row 3 minus twice row 1, since this will be 2 minus 2, which will be 0. And that will give us our new row 3. And so now the first 2 rows, they remain the same. So you can just copy those down. And then now here's where the subtraction comes in. So 2 minus 2 times 1 is 0. 1 minus 2 times -1, that is 2 plus 1, which is 3. And then 2 minus 2 is 0. So we were able to cancel or get 2 zeros on this one, which is good. And then lastly, our 9 minus 2 times 3, which is 6. So that would be 3. And so now what we had to do is, so what we can do here is, because we have 2 zeros on the last row, and they're on each end with some non-zero constant in the middle, and we want to put this in I guess in diagonals of 1, as I mentioned here. This pretty much is similar to this portion here. So now what we can do is we can switch row 1, not row 1, row 2 and row 3, and then subtract row 3 by 3. And so what you can do here is, the neat thing about this is that you can have multiple steps in one go, but the only issue here is it can become a little bit difficult if you're gonna end up doing, say, add 2 rows and then flip one and then divide another one. You have to keep track of what you end up doing. But here this is relatively simple, so all you have to do is switch R2 with R3, and then 1 over 3 R3 is going to equal to R3. And so what you end up getting is the top row stays the same. The bottom row is now the same as the second row. And then our middle row, our new middle row, would be 0, 1, 0, and then 1, because we switched them and then we multiplied it by 1/3. And so now we have this single one here, and that's very convenient because we can now eliminate this -1 and this 3 without worrying about changing the first column or the last column, since they're going to be added, multiplied, or subtracted by 0. And so we're going to go ahead and do that. And so what we're going to do is we're going to get rid of the 1. So that's just simple as adding. And so what we're going to do is R1 plus R2 is equal to R2. And so that will give us 1, 0, 1, 0, 1, 0, 0, 3, -2. And then this would be 4, 1, -3. And then to get rid of the 3 is we just subtract it by 3 times the second row. So R3 minus 3 times the second row is going to equal to our new R3. And so the top one remains unchanged. Middle one remains unchanged as well. And then the last one is the zeros are so zeros. And then we have 1 minus, oops, sorry, this one's -2. So we have 1 minus, oh, I'm sorry, we'll have 3 minus 3 times 1. So that'll just be 0. And then over here we'll have 3 times -3 minus 3 times -3. And so what we end up getting is 3. Wait, give me a second. 4, 1, 3. Okay, so this would be 0, 0, -3. Oh, -6, my bad. It'd be -3 minus 3. Yeah. Okay, see, that's more correct now. And so what we can do here now is we can make this last row into a 1 by simply divided by -1. And so we will have divide this by -1/2. R3 is equal to R3. And so have 1, 0, 0. Oops. Then 0, 0, 1. And then 4, 1. Not 6, 3. And then lastly, we can just eliminate this last one by subtracting R3. So R1 minus R3 would equal to our new R1. And so that will give us our final answer, because we have this in row reduced echelon form, which is this is as simple as it can get with this matrix. And so what we have here is 4 minus 3, which is B1. And like I said before, our answer on the right side would be exactly the same as our unknowns. So our x, y, and z would equal to 1, 1, 3. And you can check or double check this by simply plugging it back in. So we'll have 1, 1, 3. So we have 1. So for the first one, it has 1 minus 1 plus 3, which is 3. And then the second one is 1 plus 2 minus 3, which is 0. And then lastly, 2 times 1 plus 1 plus 2 times 3 would be 2 plus 1 is 3, plus 6 would be 9. And yeah, that's how you do row reduction with systems of equations. So yeah, I'll catch you in the next one.